Hi, welcome back. We're up to Lecture 4, Segment 2. And in this lecture, we're talking about summary statistics. And in this segment in particular, we're going to talk about measures of variability. So what do I mean by variability and measures of variability? Well, in the last segment, we talked about measures of central tendency, like the mean, the median, or the mode. What those measures do is they try to capture the center point of a distribution. What measures of variability do is they try to capture how much spread or how much how wide is the distribution. So the two main measures that we'll look at are standard deviation and variance. And variance is simply standard deviation squared. So standard deviation is just the average deviation from the mean in a distribution, and we'll see that mathematically in a moment. And again, variance is standard deviation squared. So this is an important formula to know. I'm assuming that most of you already knew the formula for a mean. And if you didn't know it already, it's all right. It's easy to remember. Remember, it's just the sum of the scores divided by the number of scores. So sum of x divided by n. This formula is just as important to know. You should know this off the top of your head. The formula for standard deviation and for variance. It's very similar, it's just now we're going to get the sum of deviation scores squared. That's known as the sum of squared deviation scores, or for short, sum of squares, and divide that by n. And I'll walk you through the math so you get familiar with this, because this is a really important concept going forward in statistics, is knowing how to calculate standard deviation and variance and understanding them conceptually. Okay, so if this is new to you, please spend a lot of time reviewing this segment so that you get the math down and you get the concept down. And just a word about variance before I dive into the math and an example is sometimes, especially in psychology and sometimes in sociology or in political science, variance gets a bad rap. So like I study individual differences in intelligence, for example. And a lot of times people think, oh, well, it's so horrible that this child has scored so poorly on this intelligence test or so on. But it's always important in statistics to remember that variation is natural and it's good. It's information in statistics. So look at variance with a very positive view, if you can. Because it's, as I said, it's natural, and the way to think of it in statistics is variance is information. It's going to allow for us to investigate covariance and correlation, and so on. So, and if you don't trust me, or if I'm not convincing you enough that variance is natural and variance is good, check out a guy named Darwin. He thought it was pretty good. So, on to an example. This is one of my favorite examples I developed last year because this happened in New York City, which is where I live, and it happened in professional basketball in the US, in the NBA. This is a guy called Jeremy Lin, who was not that big of a star, not a star at all actually. He's not really a top basketball player in the US, but all of a sudden he got the chance to play for the New York Knicks. So there's Jeremy Lin in Madison Square Garden. That's right there in the middle of Manhattan, just a couple of blocks from where I live. So I got caught up in what the media called Linsanity. Jeremy Lin suddenly took the NBA by storm because he started scoring a lot of points. So what we're going to do is we're going to look at Jeremy Lin's points per game over that time. It was during the winter of 2012. So what I can do is I can look at Jeremy Lin's points per game across, let's just pick out a 10-game stretch of that season in 2012. And if you start at the bottom, actually, you'll see there's just 2 points per game in that one game. And that was typical of what Jeremy Lin was doing before one of the star players on the Knicks was hurt, and Jeremy Lin had the opportunity to play. So Carmelo Anthony, who's one of the stars of the New York Knicks, he was hurt. Jeremy Lin got the opportunity to start, In his first opportunity to start, he scored 25 points. And then the next time he started, he scored 28 points, and so on. He scored 23, and I think it was around here when he scored 38 that Linsanity totally set in New York City, and we got all excited. We thought the Knicks were going to win the NBA championship. Never happened. Not happening again. Today, as I film this, the NBA Game 7 championship is happening tonight here in the U.S., and the Knicks aren't in it. But back to the topic of this lecture, we have Jeremy Lin's points per game across 10 games. We can get summary statistics from this, right? So we can get what was his average across this segment or this section of the season. So what was his average across these 10 games? And that's a common statistic in a lot of sports. So points per game, or say goals per season if you're looking at football internationally, or hockey here in the US is also big right now. So we could get just average points per game. But I also might want to know, and it's an important statistic to look at if you're looking at sort of the quality of players, is how variable are these players across a certain stretch of games. So was Jeremy Lin consistent across these 10 games, or was he sort of all over the place, having a good night one night, a bad night the next night? So first, let's calculate the mean. That's just the sum of all the scores divided by n. And I did that down at the bottom of the screen here. To get the mean, I just summed that column of points per game. The sum of that column is 227. We're averaging over 10 games, so it's 227 over 10, or 22.7. So during that 10-game stretch, Jeremy Lin is averaging 22.7 points per game. That's the mean. That's a measure of central tendency. But we want to know about his variability over those 10 games. So the way to calculate variability is variance and standard deviation. The first thing we want to do is for each game, we want to calculate what's known as a deviation score. And that's this column. These are deviation scores. So to get a deviation score, I just take how many points did Jeremy Lin score in one game and compare it to his average. So in this first row, I can take 28 and subtract his average, 22.7, and I get 5.3. So he was deviating from his average about 5.3. He was 5.3 above average that night. And so on, I can calculate each deviation score. The whole point of variability is getting sort of an average deviation. Now, I can't take the average of this column because it sums to 0. So if I summed that column, I would get 0, and divide by 10, I'd have 0. So instead, what we'll do is we'll square each deviation score. That's this last column, is the deviation scores squared. That gets rid of sign. So then when I sum the squared deviation scores, I can divide by n, and that gives me variance. So this last column, I've just taken each deviation score, squared it, and then sum all the squared deviation scores to get 922.1. If I divide by 10, that gives me 92.21. So to summarize those results, his average points per game, or mean, was 22.7. The variance, standard deviation squared, was that 92.21. It was the sum of squared deviations divided by n. For short, we're going to call that sum of squares divided by n. If we take the square root of that, then we get the standard deviation, 9.6. By taking the square root, that brings us back to the units that we started in. Remember, we had to square everything to get rid of sign when we went from deviation scores to squared deviation scores. So this last step, we take the square root. That brings us back to the units we were in, which is points per game. What this is saying is, on average, he was fluctuating about 10 points per game. Is that really accurate? Not really. He wasn't really fluctuating about 10 points per game once he had the opportunity to start, right? The standard deviation is 9.6 because I included that one game where he only scored 2 points. He didn't start that game. If we don't include that, then his standard deviation will go down. Before I do that, I just want to point out some notation. Again, I'm going to use M for mean, SD for standard deviation, SD squared for variance. That's also known as mean squares for the mean sum of square or mean squared deviations. So mean squares, sums of squares, these are important definitions to know going forward. But again, let's look at Lin and compare him to one of the top stars in the NBA, Kobe Bryant. I guess after this year, I might have to do LeBron James, but I just can't. I don't like him. Not really a big fan of Kobe either, but I'm sticking with Kobe. Let's compare Jeremy Lin during that time in the winter of 2012 to what Kobe Bryant was doing during that time in the winter of 2012. Kobe Bryant was the leading scorer at the time in the league. So if we take the 10 games that I just looked at for Jeremy Lin and we compare 10 games from Kobe Bryant during that same stretch of time, this is our output. You're now familiar with this after going through the first lab, and hopefully you're working on the first homework. What you see is here's the mean for Lin and here's the mean for Bryant. So Jeremy Lin was averaging 22.7. We just showed you how to calculate that by hand. You won't have to do that. Just plug it into R. R will give you the mean. It's 22.7. He wasn't really doing quite as well as Kobe Bryant. Kobe Bryant was averaging 26.4 points per game. But if we look at a measure of variation, so let's look at the measure of standard deviation. As we saw in our hand calculations, Jeremy Lin's standard deviation is about 10 points per game, whereas Kobe Bryant's is only about 7.5 points per game. But again, that's because I included that one game where he had just 2 points in that game, and he didn't start that game. So let's compare Kobe Bryant and Jeremy Lin if I drop that one out. So here's the R output if we just look at 9 games during that stretch, and in these 9 games, Jeremy Lin started all 9 games. Now he's doing almost as well as Kobe Bryant, 25 points per game versus 26.6, and his variability is about the same. So now it's about 7.5 to about 7.8. He's actually more consistent than Kobe Bryant across those 9 games. In that one little stretch of time in the winter of 2012, it was wonderful back then for us Knicks fans. It didn't last long. But that's the point of this little illustration, is to look at summary statistics. We can get something that's very common we know about is the average or mean, but we can also look at variability. How consistent are the scores in a distribution? Or how variable are scores in a distribution. And that's the point of calculating standard deviation and variance. So to review this entire lecture, the point of summary statistics is we can't always show our audience, or when we're writing up research for a publication in a journal or an article in a newspaper or on a website, we can't show all those histograms for all our variables. It just becomes too much information for the audience to digest. So we often want to just give some talking points, some summary statistics. And the most common summary statistics are measures of central tendency, and the most common one of those is the mean or average, but you might want to do median in the case of extremely skewed distributions. But it's also really important as you start getting into statistics, and really important for the rest of this course, to think beyond just the mean or measures of central tendency and think about measures of variability. variance is going to be a really important concept as we move forward. So it's important that you understand how to calculate standard deviation and variance, and it's important that you understand conceptually what standard deviation and variance mean and what they convey. Finally, it's important that you know the following formulas and that you could just do these by hand. Of course, we're going to do all our calculations using the R software. It's less error prone and a lot faster and convenient, right? But you should just know how to do these off the top of your head. So again, hopefully this one was review. If it's not, just give yourself some practice on it. So the mean is just the sum of all the scores divided by the number of scores. And then I gave you this one formula for standard deviation and variance. This first one is used for descriptive statistics, and that's still all we're dealing with is descriptive statistics. We're just describing what's going on in a sample. Next week, when we move to inferential statistics, we're going to use a slightly different formula for variance and standard deviation, where we'll divide by n-1, and we'll talk about that when we go into inferential statistics. And if you were very sharp, you will have noticed that the standard deviation I calculated by hand for Jeremy Lin's points per game was not exactly the same as the standard deviation that we saw in the R output. And that's because I used the formula for descriptive statistics. I divided by n, because that's all I was doing is descriptive. But the default in R is to use the inferential formula, dividing by n-1. And that's why there's that slight discrepancy, if you picked up on it. And that's the end of that segment.